space. It can vary by population, as I say, whether you're young, middle-aged, or old. And it also can vary with training. If you have additional training, you can learn to respond to different activities in different ways. And likewise, the incident, although we talk about the probability of the incident, the severity of that incident, the harm caused by that incident, can vary with a completely different set of characteristics that don't have anything to do with the probability of the event occurring itself. And so they may be completely independent in that regard. This is an example of the variability in both space and time. I did this for Dr. Watkins' benefit. This is the variation of pedestrian fatalities in rural and urban areas of function of the day of the week. So if you're walking in an urban area, you should try to do it Monday through Thursday. Okay? And avoid the drunk tanks on Friday and Saturday night. I'm still trying to figure out why Sunday's bad, but maybe walking back from church. I don't know. But rural areas have a difference, and of course in urban areas we see that there's a significantly different number of incidents that occur in urban areas. Not surprisingly, that's associated with differences in population and differences in exposure. Okay? So even though the rate may be the same, the number of incidents, which in this case is fatal accidents, could be different. Now, of course, that's an example of a daily type of situation. You can also look at the same data as a function of hours of the day, and we see where our activity or the exposure changes dramatically. There are people, in fact, walking in urban areas at 3 and 4 in the morning. It's not the most recommended situation. But most of the fatalities occur in the afternoons. Notice that it's significantly more people die in pedestrian accidents in the afternoon and evening than they do in the morning. And so some of that may be associated with activity, but some of it may also be associated with the driver's conditions who are looking at the type of circumstances. You make lots of different hypotheses. Now, as we said, and here we've been looking in terms of fatalities, but we can also look at it in terms of the exogenous variables, things that don't necessarily affect the probability of a collision, but can affect its severity. And this is an example of the same sort of information about pedestrian fatalities as a function of the speed at which a vehicle struck the individual. So your probability of suffering what we refer to as a fatality or an incapacitating injury, the A in the CAPCO scale. If you're not familiar, we have a standardized scale in the U.S., 2 different ones actually, one of which simply classifies crashes in terms of someone being killed, K. A, B, and C are incapacitating injuries, minor injuries, potential injuries, and then O, which is property damage only. So that's the CAPCO scale. There are others which are healthcare based, which we refer to as the MAIS scale, which is associated with what it did to you rather than just whether you had an injury. Makes a distinction between different parts of the body. But notice that the probability of being killed rises dramatically with speed. Now, it's not necessarily true that the incident number goes up, but the probability of injury and fatality become significantly greater with the increase in vehicle speed. Now, the question, of course, is how, we've talked about all these risk factors, how do we determine the actual risk factor? Well, we use high-level math, right? Very traditionally, we've used and said, okay, the number of incidents equals the risk times the exposure. So someone was able to do the math and concluded that a way to estimate the risk was to take the number of incidents and divide by exposure, and thus you have your risk. And that tends to give you numbers like the number of people, fatalities per 100 million vehicle miles traveled. That's a number. Or it could be, in the case of health, cancer deaths per 100,000 person years, although that's a little bit difficult. Just a little question here. How many times do you think the average American dies? think this is a trick question, right? The average American dies 2.3 times. You're looking at me kind of, yes, of course that happens. And I just gave the example right here. How many people die of cancer? Well, nobody dies of cancer. People die because the cancer caused your heart to stop, or your breathing to stop, or your brain to stop functioning, right? That's what actually killed you. So if you look at the statistics, you'll find out you died of cancer because you had cancer when you died, but you also died of heart failure. As a matter of fact, if we take the top 5 leading causes of death in the United States and we add up the numbers, it's actually bigger than the number of people who die. So, kind of reliable statistics. Okay. Now, fortunately, in transportation, we don't worry about it. A crash only happens once. Well, that's actually not true either. We actually do the other way. Why would we have to go in the other way in terms of safety data? If I crash into 3 other cars and then go off a cliff, that's one incident, right? But I can have 3 different outcomes. So we actually have more outcomes than we have incidents in transportation. So health and safety operate under different principles. All right, well, that's one example, but that doesn't tell us a great deal. It tells us something on average across the whole U.S., which is very good for telling something like a trend. But it doesn't tell us much about any type of endpoint, you know. We may, in certain cases, stratify it in a certain amount. We may separate out interstate highways from arterials versus local roads. But we have a very limited amount of stratification. We may stratify it by state and say, oh, these are the people who died in Georgia versus California. But very typically, these aggregate numbers are really used to determine from one year to another what the trend is. Now, there are other techniques. For example, we can use more stratified activity where we include vehicle type or incident type or population segment, or however we can break down the same data. We can do it in terms of stratification to determine comparative rates. But we can also use comparative methods. Okay? These are ones that essentially depend upon spatial differences at a particular time. And these are this could be example, workers versus non-workers. It might be an example of a certain aspect. Urban versus rural conditions, the U.S. versus Canada. These are ones that are for a particular time, what happens to different groups at different places. There are also time-based, which we call longitudinal methods, which are based on trends that occur over time. And these can be done, for example, before and after studies. You know, if I put in treatment, what happened, and those can be in turn done by what we refer to as naive or so-called ceteris paribus, everybody ends being equal, or Bayesian type of methods. Now, Bayesian methods have been sort of codified in the U.S. in the last decade or so by the Highway Safety Manual, which has specified a predictive method of estimating risk that takes into account certain biases. And one of the principal biases we have to deal with in safety is a problem that we call regression to the mean. For example, when we look at a problem, it varies with all the variability we've talked about. Where are you going to look for where to put in a safety process? Well, it's normally where you've had the highest risk in a recent time. But very often, that can just be due to natural variability. 5% of the places are going to be in the top 5% of the places, right? Highest. So if I go and put a treatment there, even if I did nothing, there's a very good chance that that number would be smaller later on, simply by random processes. And we call that particular bias regression to the mean. And the way we tend to correct for that is to account for those differences as a piece of information that we know. And we do that by the use of what we call Bayes' theorem, which is essentially a fancy way. There are very few things in life that have been designed pedagogically more confusing than Bayes' theorem, and that's not true. Coriolis force comes to mind, but Bayes' theorem is a very good example. Bayes' theorem really just tells us one thing, okay, is that if I found out, if I'm a betting man, okay, but I'm not terribly, and I knew that somebody got injured, right, on this particular team, I would probably say that the probability of the other team winning has changed in my mind because of this injury. Because I now have a new piece of knowledge. And all Bayes' theorem tells us is how we should adjust our estimates based on that new piece of information. For example, if we had the probability of A occurring, and that was our original guess as to what the probability was, and now we found out that, oh, B occurred, B occurred, but I noticed that the probability of both A and B occurring is a little different than what I would have guessed just A occurring. And so Bayes' theorem says, hey, what I really ought to do is make the probability, the ratio of this area to that area my new estimate. Clever, right? That's a fancy mathematical way of saying that, okay? So we're essentially trying to take every bit of information that we have in terms of trends and the like to make better estimates. And of course, if we do it properly in Bayes' theorem, we can get all kinds of research contracts and the like to pay for people who haven't figured out the simple way because they actually read the mathematician's description of Bayes' theorem, which I've taught it for some 30 years, and I still can't understand some of the descriptions of it. Okay? All right, so let's go ahead and talk about it. What are some of those factors, pieces of information that we can have that changes our viewpoint? Well, there are a whole range of them. It can be the functional class of the roadway. It can be the speeds that I'm using. It can be the topography. It can be the geometry, the horizontal and vertical curves that we're dealing with here. It can be the weather, reduced visibility. About 1.5% of the time in the state of Georgia, for example, the visibility on the roadway is less than 5/8 of a mile. That's actually comparable to sight distance in many cases, and that happens about 1% of the time. And so this is a significant factor. I can also have the pavement conditions. Wet pavement or ice conditions can affect my risk. And I also have driver familiarity. If I'm looking at a facility that's used mostly by commuters, it's different than if I'm looking at a hazard that occurs in a resort area where most of the drivers are not familiar with the territory. So I can use all those pieces of information to modify my risk factors. Now, the fancy way of putting that in terms of the highway safety manual is we create safety performance functions. Well, that's just another way of saying the base risk. That's all it says, right? The only difference is that the risk factors and the safety performance functions do not make the assumption that the exposure is linearly related to the risk. And nor should we, okay? If we have 10 times the number of cars on the road, we should not expect to have 10 times the number of accidents. Why would that be? Well, we might for single vehicle crashes, but when we have to have two crashes together, we would think the probability of two occurring randomly would basically be quadratic in the activity, right? Two randomly distributed. So we would expect the answer to be somewhere between 1 and 2 in terms of the exponential component. And that's what we tend to see between 1.4 and 1.7, depending on the like. But nevertheless, we're doing that. And of course, we also have these risk modifiers that we talked about. We're going to call them different things just to confuse people. We're going to call them crash modification factors, CMFs. That's just a way of saying, how much did this particular treatment or this particular activity change my base risk? That's all it's telling me. So now my incident, I have a slightly more complicated burden. I said the number of incidents is a function, a safety performance function of the exposure times CMF 1, 2, how many CMFs I have for particular characteristics for my treatment. Now, these crash modification factors can be less than 1, which means they make it safer, or they can be greater than 1. They make it more hazardous. For example, if my standard condition is dry pavement, and now I'm talking about ice, the crash modification factor may be 3 or 4. 3 or 4 times more likely to have a crash on icy conditions. Now, it's done very similarly in terms of how things are done in health-related characteristics. But if you did it the same way, then everybody would understand it, and that would be, so we're going to vary it in the exposure rather than vary it in the other. And so in health, we're going to talk, especially in toxicology, we're going to talk about dose response. It's actually the same thing that we just talked about. Dose is essentially the exposure, and response is the probability of an incident. But in this case, we're going to modify it in an important way. We're going to consider that exposure in this particular case also includes what we refer to as uptake, which is a rate, but also susceptibility, and that's an important consideration. In transportation, we tend to say, okay, we're going to say the risk factor is different for children versus older adults in terms of being susceptible. In health, we're going to say the exposure is different because their susceptibility is different. They're more likely for the same dosage to have an adverse impact. All right. Now we've talked about that and say that's a great thing. Now you introduced me to all of this. Let's go back and say there is a problem with the HSM. It's been a nice advancement, but the HSM methods are experience-based. That is, we have to know what the exposure was, and we have to have a statistically significant number of observed endpoints, be it a crash, be it a death, whatever it may be, whatever I'm specifying. Now, the problem with knowledge of exposure is that for very many modes, for example, bicycle modes or little scooters floating around campus, the actual exposure is very difficult to derive, very difficult to know. Okay? And likewise, for rare events, the number of events are quite small. And so as we begin to move forward to get the statistically significant number of endpoints, we have a choice of either increasing the time, which I think for bicycle crashes, what, 200 years? Is that something like that? All right. But if we increase the time we're observing, we lose the ability to talk about trends, because now we're integrating them all together. And if we increase the spatial extent by adding more and more sites, we lose the specificity of what the conditions that are present at that particular location are. So these are great methods for common occurrences, but for rare occurrences, or relatively rare occurrences, when we talk about really rare occurrences, we have this basic question: what can we do in the case of where we have limited exposure for actual endpoint data? Well, this has been addressed by other people before, and especially in health with rare diseases, and there are a variety of strategies that have been involved. The first type is what we call a case control study. In this particular case, you're working from an incident, and you're working backwards to determine the factors that may be common among several incidences. And you work backwards to estimate the frequency that these conditions occur and derive risk in that way. Now, this has been used for many years to look at very rare events. The NTSB uses this type of method to analyze airline crashes, earthquakes, type of conditions that have been done through case control studies. Now, we can also do cohort studies, in which case we decide we need to get exposure, so we can put information on a limited group of people to try to gather that cohort information, okay, and allow us to use this type of information to do it. Now, that, of course, requires an extrapolation to the overall population, which essentially means you have to be very careful in selecting your cohort if you want that to be useful. Of course, we also have what we call surrogate studies. and say you're looking at a situation where you're looking at a particular endpoint, let's say a crash, and that may not occur with very much frequency. But another event may be associated with that. For example, emergency braking, okay, rather than a crash. All of us in drivers know that you end up having to go through an emergency stop much more frequently than you're involved in a crash. And so if we can make a reasonable incident, a reasonable guess as to the ratio of the number of emergency braking events to crashes, we may be able to use that as a surrogate for estimating crash risk by looking at something that occurs more frequently. Okay. And lastly, and then this is very common, we can do engineering studies, which basically assumes that we can develop an assumed failure sequence, which will allow us to estimate the probability of a failure. And this can either be correct or insanely wrong. When NASA had, of course, never launched the space shuttle, it developed a failure sequence and concluded that the space shuttle would be lost about 1 every 10,000 launches. There would be a failure that would result in loss of crew. After they got more information, they found out that the actual predicted failure rate was closer to 1 in 100. Okay? Small difference in terms of the safety of the space shuttle. Now, what has that got to do? Well, if we talk about our 3 revolutions, okay, we don't have automated vehicles on the road. We don't have a universal. How do we estimate the safety of these motors?